I am Kobayashi from Kyoto Institute of Technology, Japan. Today, I'd like to briefly introduce my project named Development of Scalable, Highly Integrated Quantum Bit Error Correction System. And the abbreviation is QBEX. As Kitagawa-sensei mentioned, our project just started last year in 2022. So today, I mainly present our proposal to establish a fault-tolerant quantum computer. Oh, this is the outline of our project. The left figure stands for the current quantum computer from RIKEN. One of our principal investigators, QL, is developing a qubit controller. It is placed outside of our dilution refrigerator and consists of discrete parts. Its size and power is pretty much big. The right figure shows the outline of my project. For front end, it's equal to the qubit controller. We are going to develop an SoC system on chip to make the qubit controller smaller and more power efficient. Below the qubit controller, we are also developing an optical and cryo CMOS IC. The top layer is called the backend to correct errors. We are going to connect the backends with scalable networks up to 1 million physical qubits. Our project focuses on those layers above qubits. We have two goals in 2025 and 2030. For 2025, we are going to develop a prototype system for fault-tolerant quantum computer, FTQC, with around 100 physical qubits. For 2030, we are going to develop a system for FTQC that can be scalable up to 1 million physical qubits. Okay, this is the list of principal investigators of our project. We have those 5 subject research topics with 12 principal investigators, PIs. The first subject is the backend for error correction. Dr. Sano from RIKEN, Professor Kadomoto from the University of Tokyo, and Professor Osana from Kumamoto University are PIs. The second subject is a qubit controller. Dr. Miyoshi from QL is the PI. The third subject is a scalable classical quantum interface by photonic cryo CMOS ICs. There are 3 PIs, Professor Shiomi from Osaka University, Professor Shintani from KIT, Kyoto Institute of Technology, and the Professor Sato from Kyoto University. The fourth is the cryo CMOS ASIC for front-end and back-end. Professor Tsuchiya from Shiga Prefectural University, Professor Takai from KIT, and Professor Miyahara from KK and I are PIs. Unfortunately, the detail of the fifth one cannot be disclosed at the current moment, but the PI is a researcher from a fabless company in Japan. The research topic is front-end RF LSI at room temperature. The relationship between the 5 subjects is like this. These 2 subjects, subject 4 and subject 3, for cryogenic, extremely cold environments. To establish a fault-tolerant quantum computer, all 5 subjects are going to interact with each other, as shown in this figure. Then I like to move the detail of each subject. The first one is backend for error correction. The goal of this subject is to develop a backend system for error correction, scalable up to 1 million physical qubits. These 3 themes are going to be investigated by 3 PIs. The first theme is a scalable backend system for error correction by Dr. Sano from RIKEN. The goal is to prove a concept of scalable QEC, quantum error correction, with FPGA-based backend system prototype. He's going to develop an algorithm and the hardware for QEC decoder and an FPGA cluster, and also going to develop an interface with upper layer and the system architecture. This is his current progress. He developed an appropriate algorithm for QEC encoder. The current promising target is a union-find decoder. The second theme is an ASIC implementation of QEC cores by Professor Kadomoto. His goal is to develop a highly integrated low-power ASIC-based QEC core for scalability. He is going to develop an ASIC, application-specific integrated circuit, working with the FPGA cluster developed by Dr. Sano. Okay, this is his current progress and plans. He already implemented greedy and union-find decoder in HDL, hardware description language. The third theme is a dependable error correction backend by Professor Osana from Kumamoto University. He is going to develop an interconnection network for the FPGA cluster. One of the requirements of the network is low latency, and the dependability of FPGA cluster must be guaranteed. The requirement of the latency is around a few microseconds, so it is impossible to use conventional Ethernet switches since the latency of them around 700 nanoseconds. He developed the direct connection network named Kyoto. The latency measured as round-trip time of Kyoto is much shorter than the commercial Xilinx or LoRa. But the latency is still large, so he must develop a network less than 100 nanosecond latency. Then I'd like to move to the second subject, advanced qubit control frontend. Dr. Miyoshi from QL is the leader. The goal of this subject is to establish a qubit control and measurement front-end system. The measurement capability is mandatory since the qubits are now under development. This figure shows the block diagram of the qubit controller between error correction backend and the qubits. There are so many issues such as signal quality and stability, and how to synchronize neighbor qubit controls and efficient connection with backend. The current controller consists of discrete components, so its size is around 9 units, only for 4 qubits. It is placed in the room temperature, but we must put it in the cryogenic environment such as 70K or 3 to 4K for scalability. Okay, this is the current qubit controller for 4 qubits. It consists of RF front-end, analog mixer, FPGA, and AD&DA, power management, and drivers for temperature control. He's going to develop an SIP system in a package and the SOM system on a module to downsize the qubit controller. The front-end FTQC has 2 principal roles. The first one is to observe physical qubit and send error syndrome to the backend. The second is to provide feedback to logical qubits based on error correction results. The observation must be performed periodically and with low latency by using some kind of specialized hardware. It must be completed independently in the front end within T1 by 1000. It is around 500 nanoseconds. The observed syndrome information is sent to the backend. The feedback operations are gate operations such as T-gate. The latency must be minimized to accelerate the execution time of quantum programs. The network between front-end and back-end must have sufficient network bandwidth and short latency. The subject 2 is going to achieve this by the tight connection with the subject 1. So it is very difficult to implement the front end for a large number of qubits in a single unit. So the scalability must be required to control a large number of qubits at the same time. The current controller utilizes the clock source that can be scaled up to 100 physical qubits. This graph shows the results of the multiple microwave transmissions from multiple nodes with slightly different start time. The fixed delay from multiple nodes indicates that the multiple nodes are synchronized with high precision even after repeated transmission and reception. With the current front end, 100 nodes for 500 qubits can synchronize control and observation signals. He's planning to evaluate and demonstrate this to realize a more scalable mechanism to support future FTQC. And microwaves to control qubits must be low jittered. The current system incorporates a temperature sensor and a aperture element for temperature control to achieve high stability. The phase jitter over 120 seconds is within 2.5 degrees, which is sufficiently stable. But the current front end has a large footprint and suffers from manufacturing variations. In order to reduce the size and improve scalability, he plans to simplify the temperature control system and use digital signal processing. Then the third subject is explained. The goal of the third subject is to develop a scalable classical quantum interface by photonic cryogenic CMOS integrated circuits as shown in this figure. There are 3 research topics. One is cryo-optical interface, encoder and decoder. The second is a cryo-PDK. The third is a cryo-CMOS microcontroller. The subject 3 is also going to correct errors at cryogenic temperature to reduce the number of operations at room temperature. The PI of the first sim is Professor Shiomi from Osaka University. He is going to develop a cryo-optical interface. These are his milestones and challenges. He already designed a prototype chip and is going to measure the chip in cryogenic environment. This is a prototype silicon photonics chip, and he taped out a new one for 30 gigahertz bandwidth at room temperature and going to measure the performance at cryogenic temperature. The second topic is cryo-CMOS PDK. As some of you may know, the conventional transistor model, such as BSIM, has an issue of discontinuous effect at 4K. He's going to develop a new transistor model with continuous characteristics at cryogenic temperature. He's going to develop a cryo-transistor model by using measurement results of transistor array test chip in a 65 nanometer bulk CMOS process. The third topic is cryo-CMOS design platform by Professor Sato from Kyoto University. At 4 Kelvin, leakage current becomes much smaller than at room temperature. From a rough estimation, the leakage current at 4K becomes less than 1/1000 at room temperature. So this kind of dynamic circuit becomes effective. So he is going to develop a dynamic circuit libraries working at 4 Kelvin. Okay, this slide shows the setup for cryo measurement environments. This is a cryo dual for optical circuit, and this is a cryo dual with over 100 IOs for digital circuits. The last one is a cryo prober that can change ambient temperature from 10K to a room temperature. The last subject is a cryo-CMOS ASIC for front end and back end. The goal of this subject is to implement ASIC operating at cryogenic temperature to control qubits and correct errors as shown in this figure. We have these 4 topics: digital circuit, RF front-end, and DAC, digital to analog converter, and ADC, analog to digital converter. We are going to use a 22 nanometer bulk CMOS, which is scaled from 28 nanometer, since it is high performance process and cost effective. The first sim is digital circuit. I also serve the PI of this sim. We are going to mitigate FPGA-based, migrate FPGA-based design by QL to ASIC, application-specific IC. It is not easygoing. For example, reset of FPGA is all synchronous, but it must be asynchronous in ASIC. This is the block diagram of the front end. LVDS, low voltage differential signaling interface, and PLL, phase locked loop, will be developed by Professor Miyahara and Professor Tsuchiya, who are also the PI of this subject. We are also developing an error correction decoder to an FPGA. To establish an FTQC with 1 million physical qubits, we must enhance reliability, since I guess that an FTQC with 1 million physical qubits is a huge system like a particle accelerator. These papers pointed out qubits suffer from cosmic ray. So classical computers also suffer from cosmic ray. Supercomputers must mitigate soft errors. We are going to measure soft errors at cryogenic temperature. The second theme is RF front-end by Professor Tsuchiya. As I already mentioned, the current qubit controller consists of discrete ICs. It is not scalable, so there are so many challenges to develop an RF front-end at cryogenic temperature like this. This is a milestone. He is going to develop an cryo CMOS RF PDK and an RF front-end working at 10 GHz with less than 10 milliwatt power. That is the power budget at 4 Kelvin. The third topic is an automatic design and synthesis of DAC by Professor Takai. He is going to explore an appropriate architecture. The left figure and the right figures compare the difference between automatic design and automatic synthesis of DAC. In automatic design, specification and topology are input, and then optimal parameters are obtained. But in the automatic synthesis, DAC topologies are input data, and then a new DAC topology will be obtained. Okay, this is a milestone and progress. He already built an environment of high-speed simulation, machine learning using GPU, and DAC circuit evaluations. Training data are collected for automated design. Okay, this is the last thing. High-speed ADC by Professor Miyahara. These are milestones. The specification of ADC is pretty much high. He's going to develop a scalable ADC, scalable for interleaved operations, and also develop calibration techniques. He developed an ADC and a measurement environment. As for measurement, he already installed low noise analog and clock signal generators and the measurement system in cryogenic environment. He designed a comparator in 28 nanometer and going to design those circuit blocks in 22 nanometer. Okay, this is a summary of our project named QBEX. We are going to develop an FTQC with 1 million physical qubits. Our research targets are above qubit. We have 12 PIs for these 5 topics. The last topic was recently added. That's all my presentation. Thank you for listening.